All right, this is a section where we're going to find the area of a surface of revolution. It's a lot like the stuff in chapter 6 where we were finding the volume of revolution. But this time, instead of volume, we're going to find the area of the surface that we get. So here is a solid revolution. And the idea is, if to compute the surface area, we want to take it and cut it up into bands like this. I'm drawing them pretty wide on here, but of course the idea is we're eventually going to shrink those bands down to basically zero length and add all those up using an integral. So one thing here is, if you look along the band, the length of the band is going to be this, or maybe I should call it the width, but it's going to be this distance here, and that's the distance along the curve. So instead of it being dx or dy, it's going to be ds. So we'll have to use the ds that we developed in section 8.1. So let's work this out. I'm gonna draw another drawing here. Let's say we have this curve and we rotate it around the x-axis, and we'll call that a reflection. Let's draw one band on here. So we get that. So we've got this band. And we need to come up with the area of this band. All right. So let's look at a couple of things. We've got the radius of the thing, and we've got ds here. Let me try that again. So the area of the band is going to be, all right, the circumference of the thing is going to be the circumference times the width. All right, and from just geometry, the circumference of a circle is 2 pi times the radius. And the width of this thing, we've already said, is ds. So the area of the band is two pi radius times ds. And the area of the whole thing, I'll just call that the total surface area, SA, is the integral of that. You integrate 2 pi times radius times ds from A to B. So that's the formula to memorize here. Well, that and this, I guess. So let's do an example. Let's see, the first example I have is find the surface area of the sphere formed by rotating this curve from x equals -2 to x equals 2 around the x-axis. Now, I know this is a sphere because this is a semicircle, and if you rotate that around the x-axis, you're going to get a sphere. So let's draw this. So we've got y equals square root of 4 minus x squared. You rotate that around, and you get a sphere. Now I'm just going to put in one band here. The radius is going to be what? The radius is just y. So we're going to have 2 pi integral of the radius. The radius is y, but I want to do this in terms of x. Times ds. So now we've got to figure out what is ds. Well, let's see, to get ds, we've got to take the derivative of this. dy dx, I'm going to use that in notation. to take the derivative of square root of 4 minus x squared, you get 2 square root of 4 minus x squared on the bottom, and then you get the derivative of the inside function on top, minus 2x. So you get minus x over root 4 minus x squared. So that means my ds is going to be square root of 1 plus that squared dx. So let's see, if I multiply that out, or square that out, I get x squared on top, and I get 4 minus x squared on bottom. And I'm going to do one more thing here. I'm going to replace that 1, and I'm just going to do it here. I'm going to replace that 1 with 4 minus x squared over 4 minus x squared. So now my ds here is going to be, let's see, on top we're just left with 4, and on bottom we've got 4 minus x squared. Yeah. All right, so that's my ds. So I'm going to come back up here, and this was my surface area. So my surface area is going to be 2 pi integral of 4 minus square root of x squared. I said that slightly wrong, but we get that from up there, and then the ds gets replaced with square root of 4 over square root of 4 minus x squared dx. And what are our endpoints here? Our endpoints go from this point to this point, so our endpoints are negative 2 to 2. Now, this looks ugly, but nice stuff happens here. You got 2 pi minus 2 to 2. Basically, this and this cancel with each other, and we're just left with square root of 4, which of course is 2. So this integral turns into something that's actually really simple to do. So we integrate it. Well, actually, first, let's pull that 2 out front. You get 4 pi integral from minus 2 to 2 of dx. So you got 4 pi x from negative 2 to 2. Plug them in, you get 4 pi times 2 minus 4 pi times negative 2. I guess I don't really need that extra parenthesis there. So you wind up with 8 pi plus 8 pi. So you get 16 pi for your area. And if you know the formula for the volume of a sphere, the volume of a sphere is 4 pi r squared. And so if you plug in, the radius here was 2, you get 4 pi times 2 squared, 16 pi. So this example gives us something that we could do if we already knew the formula. But this would be really good if you wanted to find the surface area of just a part of this sphere. Instead of going from negative 2 to 2 and getting the whole thing, you could find just the surface area of, say, from 1 to 2. That would give you the, if you just went from 1 to 2, that would give you the surface area of this little cap of the sphere. So anyway, that's a first example, and that's actually a pretty involved one. So we'll do another example in the next video.